In the last video, I briefly mentioned that there are more degrees of freedom at high energy than at low energy. Can we intuitively understand the statement? Let's take something by my hand. Let's say this Xbox controller here. If I tap it with my finger, namely I'm putting it into a low energy scattering event, we could see that this controller behaves as a whole and nothing interesting would really happen. However, if I smash this controller into the wall really hard and putting it into a high energy collision, we could see that the microscopic composite of the controller popping out. For example, the buttons, the chips inside, the triggers, etc. It simply means that we could see more things at high energy than at low energy. However, can we concisely understand the statement? Can we quantify it? Can we say that the high energy degrees of freedom is always greater than the low energy degrees of freedom? It turns out to be no. There are certain theories that we know of would violate the conjecture I just made. So how do we understand the rough estimation of the high energy degrees of freedom that is roughly bigger than the low energy degrees of freedom? In 1988, John Cardy proposed that one can actually measure a geometric quantity, let's call it A here. The A measured at high energy is always greater than the A measured at low energy, according to Cardy's conjecture. However, Cardy couldn't prove it, at least in 4 dimensions that we lived in. It was not until 2011, Zohar Kolmogorski and Adam Schremer, they utilized 2 fundamental properties of quantum field theories, namely the probability has to conserve and the information cannot travel faster than light, to prove that A is strictly greater at high energy than at low energy. They can actually construct a monotonical decrease of A from high energy flowing to low energy, which is a stronger statement. The A here, it turns out to be positively correlated to the numbers of degrees of freedom associated to the species of particles. For example, A equals 62 times the numbers of degrees of freedoms of gauge boson squared. It was not until 2011 that human beings could fully understand that why there are roughly more degrees of freedom at high energy than low energy. For me, this a-theorem, together with its proof, is one of the most elegant, influential, and deep theorem in the modern era of theoretical physics.